We'll start by defining sensors and signal conditioning, then explore the challenges associated with high-output impedance sensors, and finally develop a practical signal conditioning solution using operational amplifiers. Before discussing signal conditioning, let's first define what we mean by a sensor. So a sensor is a device that converts a physical phenomenon into an electrical signal that can be measured and processed. Although these sensors measure very different physical quantities, they all perform the same fundamental function. They convert information from the physical world into an electrical signal. However, generating an electrical signal is only the first step. In many practical systems, the sensor output cannot be measured or processed directly, which creates the need for signal conditioning. So in practice, the raw signal produced by a sensor is often not immediately suitable for measurement or processing. Signal conditioning refers to the process of preparing a sensor signal so that it can be accurately measured, digitized, or further processed. Depending on the application, signal conditioning can involve different tasks like amplification, filtering, buffering, isolation, or linearization. In today's lecture, we'll focus on buffering because it represents the main challenge in our example sensor system. Suppose we have a sensor that produces an output voltage of 200 millivolts RMS. This does not appear to be a difficult measurement problem. However, the sensor also has an output impedance of 60 mega ohms, which is extremely high. To analyze this sensor, we can model it as an ideal voltage source in series with an internal resistance, as shown in the figure. This raises an important engineering question. Can we directly connect this sensor to a measurement system? Suppose we connect this sensor directly to a measurement system with an input impedance of mega ohm. The sensor and the measurement system now form a voltage divider. If we substitute the values in the voltage divider equation, we find that the measured voltage drops from 200 millivolts to only about 3.3 millivolts. This means that a sensor producing a relatively large signal now appears to produce a very small one, simply because of the interaction with the measurement system. Therefore, before we can accurately measure the signal, we must first prevent the measurement system from loading the sensor or altering its value. To solve the loading problem, we introduce an operational amplifier configured as a voltage follower, also known as a buffer. The purpose of the buffer is not to amplify the voltage. Instead, it isolates the sensor from the measurement system. Notice that the voltage gain of the voltage follower is equal to 1, which means that the output voltage follows the input voltage. The voltage follower has two extremely important properties. First, it presents a very high input impedance to the sensor, meaning that it draws very little current and therefore does not significantly disturb the sensor output. Second, it provides a very low output impedance, allowing it to drive the measurement system effectively. In other words, the buffer acts as an interface between a weak sensor and the rest of the measurement system. The sensor now sees almost no load, while the measurement system sees a strong low impedance source. As a result, we preserve the original sensor voltage while eliminating the loading problem. In summary, the buffer does not improve the sensor signal itself. It protects the sensor signal from the measurement system. This demonstrated an important principle in instrumentation engineering. The measurement system itself can alter the quantity being measured. To solve this problem, we introduced the voltage follower, which provides a very high input impedance and a very low output impedance. This allows us to isolate the sensor from the measurement system and preserve the original sensor signal. Although signal conditioning can also include amplification, filtering, and digital processing, we focused on buffering because it represents the primary challenge in our example. Therefore, the key message from this lecture is the goal of signal conditioning is not simply to measure a signal, but to measure it without disturbing the physical system that generated it.